The vast emptiness of space stretches infinitely, a cold, silent void that has confounded humanity for centuries. Stars flicker like distant fires in the dark, galaxies swirl in graceful cosmic ballet, and black holes linger at the edges of existence, shrouded in mystery. Yet, in the midst of all this boundless nothingness, an unprecedented discovery has emerged. It is a discovery so profound, so incomprehensible in its scope, that it threatens to reshape everything we thought we knew about the universe. It breaks the limits of imagination and scientific understanding, as though it were a revelation meant for another age, or perhaps for a completely different kind of intelligence altogether. This is not just another star, not just another distant galaxy to be catalogued. No, this is something so colossal, so beyond our expectations, that even the most advanced space telescopes, those titans of technology designed to peer into the farthest corners of the cosmos, could hardly believe what they were seeing. It is a galaxy, but one unlike any other we have discovered before. Its scale, its size, its very nature defy the very laws of astrophysics that we thought were well understood. And yet, there it is, sitting in the cosmic sea like a hidden giant that has only just come to light. As the camera zooms out, we see this moment unfold through the lens of the James Webb Space Telescope, JWST. This incredible instrument, launched into the void to capture the most elusive secrets of the universe, is the one to bring us this astonishing news. As if by sheer accident, this cosmic behemoth has been discovered, found not by chance but by design. In the detailed images captured by JWST, the universe unfolds in ways we never imagined. Here, in the dark expanse of space, something monumental is taking shape. And in this moment, we, the observers, find ourselves caught in the middle of an overwhelming mystery. What could this discovery mean for us? What does it reveal about the nature of the cosmos, and perhaps, more importantly, about the way we see our place within it? The initial reaction among the scientific community is one of disbelief. Could this truly be real? Could this galaxy, this strange new entity, be the harbinger of something even greater? There is an unmistakable tension in the air, as scientists exchange theories, calculate equations, and share their findings. Each new piece of information raises even more questions. How could something this enormous exist in the far reaches of the universe? How could it form in ways we had never predicted? And what does it mean for our current understanding of cosmic evolution? The discovery is so remarkable, in fact, that it compels us to ask the very fundamental question: how much do we truly know about the universe? For all the knowledge we've accumulated, for all the breakthroughs in astronomy and physics, how little we seem to understand when faced with the vastness of space. As we marvel at this discovery, we are forced to confront our own limitations. How can we claim to understand the universe when it continues to surprise us in such dramatic, unexpected ways? This opening moment is not just about unveiling a new galaxy, it's about a deeper reflection on the nature of exploration itself. The human thirst for knowledge is insatiable, but with every answer we uncover, we are confronted by an even larger set of mysteries. This discovery is not merely a scientific breakthrough, it's a symbol of the unknowns that lie beyond our grasp, waiting to be discovered. The emotional impact of this moment is profound. There is a certain awe that comes with witnessing something so extraordinary, but there is also a deep, unsettling fear. A fear that perhaps the more we uncover, the more we realize how little we actually know. In the background, the sounds of distant celestial winds and the hum of cutting-edge technology echo in the void, amplifying the tension. With each new image that the JWST sends back, we are left on the edge of our seats, unable to fully process what we are seeing. We are seeing the universe in ways never before possible. Yet even these new images leave us with more questions than answers. The galaxy's very existence feels like an anomaly, an outlier in the grand pattern we've tried to impose on the universe. And this, of course, is the very nature of scientific discovery. It often begins with a mystery, with something that seems out of place, and only through relentless inquiry do we begin to understand its true meaning. As we push further into this mystery, the viewer is left grappling with the same questions as the scientists themselves. What is this discovery? Why does it defy everything we thought we knew about the universe? Is this galaxy an exception, or is it part of a larger truth that we have yet to comprehend? And if it's part of a larger truth, what does that mean for our understanding of the cosmos as a whole? These are the questions that linger in the air, unanswered, like distant stars twinkling on the edge of the unknown. The emotional weight of this discovery begins to settle in. It is not just a scientific breakthrough, it is a call to action, a reminder that our understanding of the universe is far from complete. We are standing on the precipice of a new era of cosmic exploration, and this discovery may be the first of many more revelations to come. The enormity of what we have just witnessed threatens to swallow us whole, leaving us grappling with our own insignificance in the face of the infinite. As the narrative unfolds, the camera zooms in once again on the galaxy itself. It is a bright, swirling mass of light and color, a silent reminder that the universe is full of mysteries we have yet to uncover. The more we look, the more we realize that there is no end to the wonder and terror that the cosmos holds. Each new discovery brings with it new mysteries, new questions, and new possibilities. And yet, despite the awe and fear that these discoveries inspire, we cannot help but feel an overwhelming sense of wonder, a feeling that we are connected to something far greater than ourselves. And so, with the introduction of this unprecedented discovery, we embark on a journey. A journey not just through space but through the very fabric of human knowledge itself. The emotional tone shifts from uncertainty to excitement as we dive deeper into the discovery and its implications. But even as we begin to uncover its mysteries, we know that the true depth of the cosmos remains hidden, just out of reach. And as we continue to explore, we realize that we may never fully understand the universe, but the journey to understand it will shape us in ways we cannot yet predict. This moment of revelation is just the beginning. It's the spark that sets the stage for a new era in astronomy, one that will challenge everything we thought we knew. And in the end, the real question remains, what else is out there waiting to be discovered? The universe has revealed a fraction of its secrets, but it is clear that we have only just begun to scratch the surface. For centuries, humanity has gazed at the stars, striving to understand the vast expanse of space. Ancient civilizations, with their rudimentary tools, were the first to notice the endless twinkling of stars overhead, and they tried to explain it all. They built myths around the constellations, creating stories to make sense of a world they could barely grasp. Fast forward to the present, and while we've made remarkable strides in astronomy and astrophysics, the vast mysteries of the universe still evade us. What we thought we knew about the cosmos, particularly the size, structure, and formation of galaxies, was based on centuries of careful observation, data collection, and logical reasoning. But all of that was based on a limited view of a universe that was still largely hidden from us. Up until this groundbreaking discovery, the prevailing understanding of galaxies was shaped by models that seemed to fit neatly into the framework we had constructed. We had come to see galaxies as relatively predictable structures. Most galaxies, it seemed, followed similar patterns of evolution and behavior. They were born in a specific way, matured over billions of years, and, for the most part, behaved according to the same set of cosmic rules. The Milky Way, our own galaxy, served as a model for others. Galaxies were systems of stars, gas, and dust bound together by gravity. Some were elliptical in shape while others were spirals like our own. Some were irregular, but they still adhered to general patterns that we believed were universal. The science behind this was grounded in a solid foundation of observational data. Our understanding of galaxies had been informed by decades of research and technological advancement. From the first telescopes that allowed us to peer into the night sky to the groundbreaking discoveries of Hubble and the development of modern space telescopes, we had come to believe we understood the basic mechanics of the universe. We knew about the life cycles of stars, the formation of planets, and the ways in which galaxies collided and merged. We believed we had a clear understanding of dark matter and dark energy, the invisible forces that shaped the universe in ways we could only guess at. And for a time this was enough. But what we didn't realize was just how little we truly understood. The laws that govern the cosmos seemed to be universal, and scientists had begun to piece together a story of galactic formation and evolution that made sense within the confines of what we knew. Yet, the more we learned, the more we realized how many gaps still existed in our understanding. Our models of the universe were based on a set of assumptions, built from the knowledge available at the time. We believed, for example, that galaxies formed in a relatively predictable way, merging and evolving over time. We thought that the rate of star formation, the distribution of dark matter, and the growth of supermassive black holes followed clear, comprehensible patterns. Then came the James Webb Space Telescope. Its launch into space promised to revolutionize our understanding of the universe, to peer deeper into the cosmos than ever before. JWST was built to look further into space and further back in time than any of its predecessors like Hubble. This new instrument had the power to uncover galaxies that had never been seen before, shining a light on the early stages of the universe. But no one, not even the most optimistic scientists, could have anticipated what it would reveal. As we adjust our perspective to the new information pouring in from JWST, we realize just how much we had assumed about the universe. Galaxies, in our previous understanding, were not supposed to look like this. This new discovery, the galaxy that challenges everything we thought we knew, doesn't fit the models. It defies the expectations we had built over decades of research. It stands as an anomaly, an outlier that forces us to question the very assumptions on which our entire framework was built. The discovery has left the scientific community in a state of disbelief and wonder. For instance, the size of this galaxy is unlike anything we have encountered before. While galaxies were thought to vary in size, this one is on an entirely different scale. It's far larger than what any models would predict, and its formation appears to have occurred in a way that no one had expected. We had believed that galaxies formed in a gradual, predictable way, slowly gathering stars and gas over billions of years. But this galaxy seems to have appeared almost fully formed, in a way that challenges everything we thought we knew about the birth of galaxies. And then there's the composition. Galaxies were supposed to follow certain patterns in terms of their stars, their gas, and their dark matter. But this discovery has shown that the materials inside this galaxy are in ratios that don't align with our current models. Some scientists even question whether this galaxy's formation happened in a way that no other galaxy has, or whether it's an extreme example of a process we simply don't yet understand. The very idea that a galaxy could behave in ways that don't fit our established rules is both thrilling and unsettling. It opens up the possibility that the universe has been hiding entire classes of galaxies that don't follow the rules we thought were universal. This revelation forces us to reconsider what we know about the timeline of the universe itself. Galaxies were thought to have taken billions of years to form, to evolve into their current shapes and sizes. But the new galaxy discovered by JWST may have formed much more rapidly than we believed possible. How could such a vast, fully formed structure exist so early in the universe's history? The discovery raises the possibility that our understanding of the cosmos is far more incomplete than we ever imagined. And it's not just about size and structure. It's also about how galaxies interact with the forces that shape them. This new galaxy has unusual characteristics in terms of how it responds to gravitational forces, how it holds its stars in place, and how it interacts with its surrounding environment. It seems to behave in ways that were thought to be impossible, and its behavior poses a series of new questions that no one had considered before. How can a galaxy this large exist without breaking the laws of gravity? Could the dark matter we've relied on to explain cosmic behavior be something entirely different? This new galaxy has forced scientists to confront the uncomfortable reality that our current models of the universe may be incomplete or worse, entirely wrong. It has reminded us that the universe operates on a scale and according to principles that we have yet to fully grasp. Our understanding of galaxies and the forces that shape them has been built on a foundation of assumptions, and this discovery has cracked that foundation wide open. What we thought we knew about the universe is being called into question, and this leaves us with a sense of wonder and fear. How much of the universe is still out of reach, hiding in plain sight, waiting to be discovered? As the scientific community begins to analyze the data from JWST, they are faced with a stark realization. The universe is far stranger, far more complex than we ever imagined. The discovery forces us to look back at the way we have built our understanding of the cosmos and ask whether we were too quick to draw conclusions, too eager to impose order on the chaos. This new galaxy is not just a scientific curiosity, it is a wake-up call, a reminder that the universe will always have more to show us. And the deeper we look, the more we realize how much remains hidden from our view. In this moment, as we stand on the precipice of new knowledge, we are left with a sense of both awe and uncertainty. The story of the universe is far from over, and this discovery is just the beginning of a new chapter in our understanding. We may have thought we knew where we stood in the grand cosmic scheme, but the universe is reminding us that we are still in the early stages of this journey. As we look toward the future, we can only wonder, what else lies out there waiting to defy everything we thought we knew? It began with a single, almost imperceptible anomaly, a flicker in the darkness of space that no one could have anticipated. The vast, boundless sky, where billions of stars and galaxies are scattered like forgotten dreams, was suddenly disturbed. A small team of scientists, hunched over monitors and control panels, began to notice something in the data from the James Webb Space Telescope that didn't quite fit. At first, it was subtle, almost too easy to overlook. But as they zoomed in, adjusted the filters, and refined the measurements, the truth became undeniable. A new galaxy had appeared on their screens. But this wasn't just any galaxy. This was something altogether different, something that defied every expectation they had. The discovery wasn't just exciting, it was almost unfathomable. The first images sent back by JWST revealed an enormous, sprawling mass that seemed to emerge fully formed, a complex system of stars and nebulae whirling together in a dazzling display of cosmic light. The galaxy, captured in stunning detail, was unlike anything they had ever seen. The sheer size of it alone was enough to stop even the most seasoned astronomers in their tracks. Its dimensions stretched far beyond what current models had predicted for galaxies of its age. It was, in essence, a paradox, too large, too complex, and too far along in its evolutionary timeline to fit within the conventional theories of galaxy formation. But it wasn't just the size that baffled scientists, it was the composition. Galaxies, they had thought, followed a set pattern. A slow, gradual process of star formation, the swirling of gas and dust pulled together by gravity. Over billions of years, galaxies coalesced, evolved, and grew, each one shaped by the fundamental forces of the universe. But this new galaxy seemed to break all of those rules. It appeared almost fully formed, as though it had sprung into existence fully realized. A mature, vibrant cosmic entity, showing signs of complex interactions and dynamics typically seen in much older, more evolved galaxies. The very existence of such a galaxy raised immediate questions. How could something this massive have come into being so quickly? What had driven its formation? And why did it look so different from the galaxies that had come before it? The team's reactions were a mixture of awe, disbelief, and even fear. They had trained their entire careers to understand the universe, to uncover its mysteries, and yet, here was something that pushed the boundaries of their comprehension. How could it be? How could a galaxy exist in such a state of evolution so early in the universe's history? The excitement was palpable, but so too was the unease. The implications were far-reaching, and no one quite knew what to make of the discovery yet. There was a sense of hesitation in the air, as if they were standing at the precipice of something much larger than themselves. Could this discovery be a fluke? A mistake? Or was it, as some were starting to suspect, a key that unlocked a deeper truth about the universe? For the public, news of this discovery felt like something straight out of a science fiction novel. How could something like this exist in a universe we thought we understood? The media frenzy that followed was swift, with headlines proclaiming the unbelievable galaxy and the discovery that changes everything. The discovery captured the imagination of millions, sparking questions about the nature of space, time, and existence itself. This galaxy, which had once been invisible, hidden in the vastness of the cosmos, was suddenly thrust into the spotlight, its mystery attracting both wonder and skepticism. The team of astronomers, meanwhile, began the painstaking process of analyzing the data. They worked day and night, refining their calculations and rechecking their instruments. Every time they thought they had an answer, a new question arose. It was a relentless pursuit, a race against time to make sense of a discovery that seemed to be beyond comprehension. The mystery deepened as they started to realize that the galaxy was far older than they had expected. The light emitted from it showed evidence of stellar processes that were thought to take place only in galaxies much older than this one. How could it have formed so rapidly? Could the laws of physics be different in this part of the universe, or was this galaxy a harbinger of an entirely new understanding of cosmic evolution? As they delved deeper into the galaxy's features, they discovered something even more perplexing. The galaxy appeared to be far more stable than they would have predicted, with a high level of organization and structure. Galaxies are not static. They are dynamic, constantly shifting, colliding, and evolving. But this galaxy seemed to be frozen in time, as though it had reached a point of stability far earlier than expected. It didn't seem to be in the process of forming, nor was it breaking apart. It simply existed, a gigantic, intricate machine that ran on cosmic principles unknown to us. The image of this galaxy, suspended in time, was at once beautiful and haunting. At the same time, the team began to realize that this discovery was not an isolated event. They started to wonder if there were more galaxies out there like this one, hidden in the unseen reaches of space, waiting to be uncovered. What if this galaxy wasn't an anomaly but a sign of something far larger? What if the laws of galactic formation were far more complex and diverse than we had ever thought? What if there were entire classes of galaxies that had gone unnoticed, simply because we didn't have the right tools to see them? This realization opened up new possibilities that were as exhilarating as they were terrifying. The more they learned, the more they realized that the very nature of the universe was far more complex than they had imagined. The discovery was not without its skeptics, of course. As with any groundbreaking revelation, there were those who questioned the data, who doubted the conclusions being drawn. Some believed that the initial images had been misinterpreted, that there was a more mundane explanation for the phenomenon. Others posited that the galaxy might be the result of a gravitational lensing effect, an illusion created by the bending of light as it passed through massive cosmic objects. But the more the scientists dug, the more evidence they found to support the idea that this galaxy was real, and that it was far more than a mere optical illusion. The tension was palpable as the scientific community tried to make sense of what they were seeing. Could it really be true that we had discovered a galaxy so different from the ones we knew? Could the very foundations of our understanding of cosmic evolution be about to collapse? As the images from JWST continued to pour in, the questions only multiplied. The sheer size of the galaxy, its complex structure, and its unexpected stability made it clear that we were dealing with something extraordinary. And yet, as exhilarating as this discovery was, it also filled the team with a sense of dread. A dread that stemmed from the realization that everything they had assumed about galaxies, everything they had built their careers upon, could be wrong. As the analysis continued, the questions grew more profound. Was this galaxy a unique anomaly, or was it a glimpse into a completely new class of cosmic objects? What did its existence mean for our understanding of the universe, and how would it change our theories of galaxy formation? What other secrets lay hidden in the farthest reaches of space, waiting to be uncovered? These questions weighed heavily on the minds of the astronomers, but they also ignited a fire within them, a desire to push further, to seek out the unknown, and to uncover the deeper truths that lay hidden in the stars. This was more than just a discovery. It was a moment of transformation for science itself. It was a turning point that would forever alter the way we understood the cosmos. For every question that was answered, 10 more appeared, and the journey toward those answers had only just begun. The galaxy that emerged from the darkness of space was not just a new discovery, it was a sign that we were on the cusp of a new era in our exploration of the universe, a new chapter in the endless story of the cosmos. And as the team of astronomers prepared to delve deeper into the mystery, they knew one thing for certain. The universe had just revealed a fraction of its vastness, and what lay ahead was more than they could possibly imagine. In the world of scientific discovery, there's often a sense of familiarity, an understanding that the tools we've created are sufficient to probe the universe. For decades, astronomers have relied on telescopes, both ground-based and space-based, to peer into the cosmos. With each advancement in technology, it seemed that we were inching closer to the ultimate truth of the universe. The Hubble Space Telescope, with its sharp eyes on the heavens, had already given us stunning views of distant galaxies, nebulae, and the mysterious forces that govern them. Yet even Hubble, with all its greatness, was limited by its position in space, the range of light it could capture, and its sensitivity to the distant reaches of the cosmos. Enter the James Webb Space Telescope, JWST, a project that had been years in the making, one that promised to revolutionize our understanding of the universe. JWST was designed to see deeper into the cosmos, to peer further back in time than ever before. The anticipation surrounding its launch was nothing short of immense. This telescope, a marvel of engineering, had the power to capture infrared light, allowing it to see through cosmic dust and gas that had once obscured our view. It could observe the universe as it appeared billions of years ago, providing us with a window into the early stages of the cosmos. But even as scientists were preparing for the unprecedented insights JWST would offer, they couldn't help but acknowledge the limitations of technology. No matter how advanced, every tool has its boundaries. JWST, for all its cutting-edge capabilities, could only reveal what was within its reach. It was not a magic bullet, but a highly specialized instrument that could answer specific questions while leaving others unanswered. It could give us breathtaking images and data, but it could not solve every mystery of the universe. This reality, the acknowledgement that no single instrument can fully uncover the cosmos, was something that every scientist grappled with. As powerful as JWST was, it could only push the boundaries so far. When the first images from JWST started to stream back to Earth, they were nothing short of extraordinary. The clarity, the detail, and the richness of the data were unparalleled. Galaxies that had been mere smudges in previous observations were now vivid, three-dimensional structures, revealing their complexity and beauty in stunning detail. The telescope had already begun to reveal parts of the universe that were previously hidden, taking us to the very edge of cosmic history. Yet, with all its brilliance, JWST uncovered something that even its creators hadn't fully expected. A galaxy so vast, so massive, and so far along in its development that it appeared to break every rule we thought we understood about the universe. The sheer size of the galaxy revealed by JWST was one of the first things that baffled scientists. Existing models of galaxy formation, honed over years of study and observation, simply didn't account for a galaxy of this magnitude. According to current theories, galaxies took billions of years to form and evolve. They started out as small, irregular clouds of gas, which eventually coalesced under gravity to form the beautiful spiral and elliptical galaxies we observe today. These galaxies followed a predictable life cycle, with star formation gradually slowing as time passed and older stars died off. Yet this new galaxy, captured in the first images from JWST, was too large, too well formed for this model to make sense. It was as though the universe had decided to throw out the textbook and come up with something entirely different. The initial reaction to the discovery was one of shock and disbelief. How could this galaxy exist in such a mature state so early in the universe's history? Even the most advanced theories of cosmic evolution could not explain its rapid formation. For years, astronomers had believed that galaxies formed over time, slowly building up mass and structure through gradual processes. But this galaxy seemed to defy that model, appearing to have emerged fully formed, as if by some cosmic miracle. It was a discovery that shook the very foundation of our understanding of the universe. As astronomers began to process the data, they quickly realized that the galaxy's existence was not just a question of size, it was also a question of composition. Galaxies, as we understood them, had a certain structure, with stars, gas, and dust arranged in predictable patterns. They were systems that adhered to the laws of physics we knew. But this new galaxy wasn't following the rules. Its composition seemed to be different from anything previously observed. The distribution of stars, gas, and dark matter didn't align with expectations. In fact, it appeared that the galaxy was more stable, more organized, than we would have predicted for a galaxy of its age. This posed a new challenge for the scientists involved. How could they explain the galaxy's unusual composition? Could the laws of gravity, star formation, and dark matter be different in this region of space? Or were we simply overlooking something fundamental about how galaxies form and evolve? These questions weren't easily answered. They hinted at the possibility that our current models of the universe, no matter how sophisticated, were incomplete. Perhaps we had missed something fundamental, something that would force us to rethink everything we thought we knew about cosmic evolution. This realization wasn't just a scientific puzzle, it was a philosophical one. The discovery revealed the limitations of human knowledge. It reminded us that the universe, vast and incomprehensible as it is, operates on principles far beyond our current understanding. No matter how advanced our technology becomes, no matter how brilliant our minds, there will always be mysteries that remain just out of reach. And while JWST has given us an unprecedented look at the universe, it has also revealed the stark reality that we are still only scratching the surface of the cosmic story. The emotional weight of this discovery was palpable. There was a sense of awe at what had been achieved, but also a deep sense of humility. The universe, it seemed, was far more complex, far more intricate than we had ever imagined. The discovery of this galaxy, which had initially seemed like a breakthrough, was also a reminder of how much we still didn't know. And this was not a defeat, but an invitation to delve deeper, to expand our theories, to explore new avenues of inquiry. In the midst of this uncertainty, there was a renewed sense of determination among scientists. The limitations of current technology were evident, but that didn't mean progress had stalled. On the contrary, the discovery of this strange galaxy was the beginning of a new chapter in cosmic exploration. It highlighted the need for more advanced instruments, more precise observations, and most importantly, a deeper understanding of the universe's mysteries. As JWST continues its mission, it will undoubtedly uncover more galaxies, more secrets, more anomalies that challenge our current models. And with each new discovery, we will be forced to adapt, to evolve, and to reconsider the very nature of the universe. The limits of current technology are not something to fear, they are something to embrace. They are a reminder that science is not a finite journey but an ongoing process of discovery, one that will continue for as long as we dare to ask questions. This galaxy, so large and so strange, is not just a challenge to our understanding of the cosmos. It is a challenge to our imagination, our creativity, and our willingness to question everything we thought we knew. The limits of technology, as daunting as they may seem, are simply the beginning. Every new discovery is an opportunity to break through those limits and venture further into the unknown. As we look ahead, the discovery of this galaxy marks a pivotal moment in the history of astronomy. It is a reminder that no matter how advanced our tools become, there will always be more to learn, more to explore, and more to discover. The limits of our technology may constrain us, but they also propel us forward. And with each new advancement, we inch closer to understanding the mysteries of the universe, mysteries that, just a few years ago, seemed beyond our grasp. The universe is vast and its secrets are many, but with every new discovery, we grow a little closer to understanding it all. And perhaps, in the end, that is the true beauty of science. It is not the answers we find, but the questions we continue to ask. The discovery of this extraordinary galaxy, so much larger and more developed than anything we expected, presents a critical juncture in our understanding of cosmic evolution. For years, the prevailing theories about how galaxies form and evolve had been based on a set of assumptions about time, scale, and the physical processes at play in the universe. These assumptions, while rooted in decades of observational data and careful study, were built on a linear model of cosmic development, a model that assumed galaxies followed a predictable, almost clock-like evolution. From the moment galaxies were first thought to emerge out of the primordial soup of the universe, it was believed that they grew in stages. Small, irregular clouds of gas coalescing into more structured, mature systems, gradually accumulating mass and stars over billions of years. This gradual process was the accepted narrative, until now. This newly discovered galaxy shatters that narrative. It doesn't fit into the carefully constructed models of galactic evolution. It's too massive, too well-formed for its age. According to everything we thought we knew, a galaxy of this size shouldn't exist this early in the history of the universe. This revelation opens up a whole new set of questions, forcing scientists to confront the limitations of their models and their assumptions about how the cosmos evolves. The magnitude of this galaxy's discovery is that it calls into question the entire framework of cosmic evolution. If galaxies can emerge in a mature, fully formed state much earlier than we thought, what else might we be missing in our understanding of the universe's origins? Perhaps, we wonder, the process of galactic formation is not as linear as we once believed. Perhaps galaxies don't all follow the same template. If this galaxy, a colossal entity that appears almost fully formed, is not an exception but part of a larger cosmic truth, then how many more galaxies like it are out there waiting to be discovered? The very nature of the universe could be far more complex, more diverse than the simple models we've relied upon for so long. This discovery forces us to reconsider the role of time in the formation of galaxies. The traditional view suggested that galaxies grow slowly over eons, building their structures and systems gradually, influenced by the forces of gravity, dark matter, and star formation. But this new galaxy doesn't seem to conform to that narrative. Its formation appears to have occurred on a much faster timescale, perhaps in a way that we didn't understand. The question that arises is not just about how this galaxy formed, but also about the fundamental nature of cosmic time itself. What does it mean for our understanding of the universe if galaxies can form in such a compressed time frame? The implications extend far beyond galaxies alone. If this new galaxy exists as a testament to the faster evolution of cosmic structures, what does that mean for our understanding of the broader cosmic timeline? The universe itself, after all, is a story of evolution. Stars are born, live, and die in cycles that stretch over billions of years. Planets form and decay. Black holes devour and merge. And galaxies, the fundamental building blocks of the universe, are no exception to this ongoing process. But if this galaxy, which appears to be far older than its supposed age, exists as evidence of an accelerated evolution, it could indicate that the universe operates in more ways than we can presently grasp. This challenges not only our conception of time but our understanding of the very forces that shape the cosmos. In particular, the discovery raises important questions about dark matter and dark energy, two of the universe's greatest mysteries. Dark matter, the invisible substance that provides the gravitational foundation for galaxies, has long been thought to be a stable, predictable force that shapes galaxies in the background of cosmic evolution. Yet, if galaxies can form in such an unexpected manner, could dark matter behave differently than we thought? Could it play a more active role in the formation and growth of galaxies, potentially accelerating their development in ways we hadn't considered? Likewise, dark energy, the enigmatic force responsible for the accelerated expansion of the universe, may also be involved in this new model of cosmic evolution. Could it be that dark energy's influence extends beyond the expansion of space itself, affecting the growth and formation of galaxies? This discovery, in a way, opens up more questions about the nature of these unseen forces, inviting a new era of research and exploration into the fundamental forces that govern the universe. What's more, the sheer size and complexity of this galaxy challenge the idea that galaxies are isolated entities that evolve independently of one another. In the current understanding, galaxies are thought to grow and mature in isolation, following their own individual timelines. Yet, in a universe as vast and interconnected as ours, could it be that galaxies are influenced by their neighbors in ways we have yet to understand? The idea of galactic mergers has long been a part of our cosmic model, but what if galaxies could form more rapidly or in more intricate ways through these interactions? Could this new galaxy have been influenced by the gravitational forces of nearby systems, or perhaps even by the unseen forces of dark matter and dark energy interacting in ways we cannot yet comprehend. This is where the discovery touches on something deeper, the very nature of cosmic complexity. For centuries, we've sought to simplify the universe, creating models that break the cosmos down into easily digestible concepts. Galaxies are born, evolve, and die. Stars form, live, and explode. The universe, it seems, has always been thought of in terms of a tidy, predictable process. But this galaxy, with its unexpected size and formation, reveals that the universe may be far more intricate, more multifaceted than we had realized. Perhaps there are processes at play that we haven't even begun to understand. The galaxy we've just discovered may be a clue to the complexity of the cosmos, a complexity that challenges our desire for simplicity. The emotional weight of this realization is profound. It shifts the way we perceive the universe, nudging us from a place of certainty into one of wonder and uncertainty. It challenges the very way we approach science, urging us to embrace the unknown and to rethink our assumptions. For years we believed we had the universe figured out. Now, with the discovery of this remarkable galaxy, we are forced to acknowledge that we may have only scratched the surface of cosmic understanding. We are standing on the edge of a new era of discovery, one that will challenge our fundamental beliefs about how the universe works. In the wake of this discovery, there is a growing sense of anticipation. If this galaxy is a sign of a larger, more complex cosmic narrative, what else is out there? What other surprises does the universe have in store for us? This galaxy is not just an anomaly, it is a harbinger of the unknown, a reminder that there is so much more to the universe than we can possibly comprehend. The old models, once thought to be unshakable, are crumbling before our eyes. And as we enter this new era of cosmic exploration, we realize that the journey ahead is one of boundless possibility. This is the essence of scientific progress. With each discovery we are forced to look beyond what we know, to question our assumptions, and to embrace the vast, uncharted terrain that lies ahead. The discovery of this galaxy doesn't just reshape our understanding of galactic evolution, it challenges the very foundation of how we view the universe itself. And as we move forward, we are reminded that the universe is not a puzzle waiting to be solved, but a vast, living mystery, one that will continue to unfold in ways we can only begin to imagine. The old paradigm is gone, and a new one is emerging. The cosmos, it seems, is far stranger and more wondrous than we ever thought possible. The discovery of a galaxy that defies all expectations raises profound questions not just about how galaxies form, but about the very nature of the universe itself. For decades, scientists have operated under the assumption that the Big Bang Theory was the foundational model explaining the origin and evolution of the universe. According to this widely accepted theory, the universe began from an extremely hot and dense singularity roughly 13.8 billion years ago and has been expanding ever since. The Big Bang Theory neatly explains the distribution of galaxies, the cosmic microwave background radiation, and the observed redshift of distant galaxies. It's a cornerstone of modern cosmology. But now, with the discovery of this unexpectedly large and mature galaxy, one that seems to have formed too quickly for its age, scientists are beginning to ask a much more fundamental question. Does this galaxy undermine the very foundation of the Big Bang Theory? The Big Bang model rests on certain assumptions, one of the most critical being that galaxies, stars, and cosmic structures develop over time, with early universes populated by small, irregular clouds of gas that slowly coalesced into larger and more complex systems. It suggests that the early universe was a chaotic, turbulent place, where gravitational forces began to pull matter together to form stars and galaxies, gradually giving rise to the structured universe we see today. This process was thought to take billions of years, with the first galaxies forming relatively late in the history of the universe. But if a galaxy of such enormous size and complexity can exist so early on, then the timeline of cosmic evolution may need to be completely rewritten. What if galaxies could form more quickly than the Big Bang Theory suggests? And if they can, what does that mean for the universe's expansion and early formation? The implications of this discovery for the Big Bang Theory are far-reaching. If the universe's evolution isn't as slow and gradual as we once thought, it would force a major reconsideration of the timeline of cosmic history. In the traditional view, after the Big Bang, the universe went through a series of stages, starting with a hot, dense phase in which particles, radiation, and light were all in a chaotic state, eventually cooling down to allow matter to form. The first stars ignited roughly 100 million years after the Big Bang, and galaxies began to form a few hundred million years later. These structures then continued to evolve over billions of years. But the discovery of this galaxy challenges the assumption that the early universe was incapable of forming such massive and mature systems so quickly. One possibility that arises from this new discovery is that the processes that govern galaxy formation may have worked faster than previously thought. Perhaps the growth of galaxies didn't follow the slow, gradual pattern we imagined but instead involved bursts of rapid formation, where gravitational forces and other cosmic dynamics allowed for quicker coalescing of matter into complex systems. This would drastically alter our understanding of the pace of cosmic evolution, implying that galaxies, stars, and possibly even planets could have formed much earlier in the universe's history. If such a galaxy can exist so early, could the formation of galaxies be a far more rapid process than the Big Bang model suggests? This forces us to reconsider the nature of early cosmic evolution, and in turn challenges the very foundations of the Big Bang theory. It also brings up questions about the conditions necessary for such rapid formation. For a galaxy to grow so large and mature so quickly, certain cosmic conditions must have been in place from the very early stages of the universe. Could the laws of physics be different in the early universe than we've assumed? Perhaps the forces that govern the universe's expansion, gravity, dark matter, and dark energy, acted more efficiently or in ways we don't yet fully understand. Could it be that our models of cosmic inflation, the period of rapid expansion just after the Big Bang, need to be refined or revised to account for the possibility of more rapid galaxy formation? The discovery of this galaxy challenges not only our assumptions about time but also our understanding of how the fundamental forces of the universe interacted in those formative moments. Another significant implication is the question of how quickly the universe can evolve. In our current view, galaxies form over billions of years, with stars dying, merging, and evolving over extremely long timescales. But if this newly discovered galaxy is a case of rapid formation, it might suggest that cosmic evolution doesn't always occur in slow, steady increments. Instead, the universe might have periods of rapid change, punctuated by moments of relatively still cosmic time. The idea of bursts of cosmic activity challenges the long-standing view that the universe has always been in a steady state of gradual change. What if the universe itself operates in cycles of faster and slower evolutionary periods? This new galaxy may not be the only example of this type of accelerated evolution. There could be more hidden in the farthest reaches of space, waiting to be discovered. The implications of this discovery could also extend to our understanding of the early universe's cosmic dark age, the period after the Big Bang when the universe was filled with neutral hydrogen gas and stars had yet to form. During this era, the universe was opaque and light from distant sources could not travel freely. The first generation of stars, known as population 3 stars, were thought to have played a key role in breaking this cosmic darkness. Their formation marked a turning point in the evolution of the universe. But if this new galaxy, which appears to be far older than it should be, formed so early, it could mean that the timeline of the cosmic dark age needs to be re-evaluated. Could stars have formed earlier than we thought? Could the first galaxies have arisen from different processes than the models suggest? Furthermore, this discovery opens up the possibility of rethinking the role of dark matter in the formation of galaxies. Dark matter, the invisible substance that makes up most of the mass in the universe, is thought to play a critical role in galaxy formation by providing the gravitational glue that holds galaxies together. In our current models, dark matter was essential in creating the first seeds of galaxies, helping them grow over time. But if galaxies could form more rapidly than we expected, perhaps dark matter behaves differently in the early universe than we thought. Could it be that dark matter's influence on the formation of cosmic structures was more immediate and intense than previously believed? Could there be other forms of matter or energy that we haven't discovered yet, which are responsible for facilitating rapid galaxy formation? This new galaxy's existence suggests that dark matter and potentially other forces may be more dynamic in the formation of galaxies than we have realized. As scientists wrestle with the implications of this discovery, the need for new models and theories becomes increasingly clear. The Big Bang theory, while immensely successful in explaining many aspects of the universe's history, may no longer be a complete description of cosmic evolution. The idea that the universe expanded from a singular point and followed a predictable trajectory over billions of years is facing new challenges, especially when evidence points to phenomena that don't neatly fit into this framework. This does not mean that the Big Bang theory is dead, but rather that it must evolve. Perhaps what we are seeing with this galaxy is a missing piece in the puzzle, a clue that points toward a more complex and nuanced picture of the universe's early history. The discovery invites us to explore new avenues of research, to question the assumptions we've taken for granted, and to think more deeply about the universe's origins. We are now forced to reconsider the timelines, mechanisms, and forces that shape the cosmos. The journey of discovery is far from over, and the very nature of the Big Bang Theory itself is up for re-evaluation. What we once thought we knew about the universe's birth may be just the beginning of a much larger, more intricate story. And as we continue to explore the unknown, the universe continues to reveal its mysteries, pushing the boundaries of our knowledge and understanding. The discovery of this extraordinary galaxy opens a portal into the most profound mystery of all, the true nature of the early universe. For centuries, scientists have looked to the stars as a way of understanding the origins of everything that surrounds us. The universe, with its intricate structures and vast, untold expanses, holds within it the answers to questions that have lingered since the dawn of human curiosity. Yet, the deep past of the cosmos has always been elusive. The farther back we look, the less we seem to know. And this new galaxy, with its unexpected size and complexity, has thrown open the doors to that hidden chapter in cosmic history, pushing us to question everything we thought we knew about the formation and evolution of the universe. The James Webb Space Telescope's observations have allowed us to peer further into the universe than ever before, opening a window into the cosmic past. The early universe, particularly the period known as the Cosmic Dawn, is a time of great uncertainty. It is a time we cannot directly observe but only infer through the relics and traces left behind by the universe's first galaxies and stars. Before the arrival of JWST, our understanding of this era was largely speculative. We knew that the first galaxies formed a few 100 million years after the Big Bang, but the exact mechanisms of their formation, the pace at which they emerged, and how they interacted with their environment remained a mystery. This galaxy, captured so vividly by JWST, has changed that. It is no longer just a distant speck of light in a faraway corner of the universe. It is a tangible clue, a marker that hints at the true nature of the early universe. What makes this discovery even more astonishing is that the galaxy appears to be far more developed than it should be at such an early stage. The implication is that there was something extraordinary happening in the first few 100 million years of cosmic history, something that propelled the formation of galaxies in ways that current models could not have anticipated. Before this discovery, scientists had assumed that the formation of galaxies was a slow and gradual process, starting with tiny clouds of gas and dust, which over billions of years, coalesced under gravity to form more complex structures. This was the accepted narrative for how the universe matured. But the galaxy revealed by JWST doesn't follow that model. It is already a fully formed, massive entity, with a level of complexity that should not exist at such an early point in cosmic history. The galaxy is already exhibiting the kinds of stellar processes that were thought to be the domain of much older, more mature galaxies. Its formation appears to have occurred on a much faster timescale than predicted by conventional theories. But how could that be? What was happening in the early universe that allowed such a rapid emergence of complex structures? To understand the magnitude of this discovery, it's important to reflect on the era of cosmic history this galaxy represents. The universe, after the Big Bang, went through a series of phases, each marked by key milestones in the development of cosmic structures. The first few 100 million years, known as the Cosmic Dark Age, were a time of relative darkness. After the initial burst of expansion, the universe was filled with hydrogen and helium gas, but no stars had yet formed to light up the sky. It was a period of cosmic infancy, where the conditions were too chaotic for light to travel freely across the universe. This dark era was followed by the formation of the first stars, known as population 3 stars, which were unlike anything we see today. These massive, hot stars were likely composed entirely of hydrogen and helium, and their birth marked the end of the Cosmic Dark Age and the beginning of the Cosmic Dawn. The formation of these first stars triggered a process called reionization, where the energy from these stars ionized the surrounding gas, allowing light to travel freely for the first time. This period was crucial in shaping the universe as we know it. It is also the period during which the first galaxies began to take shape. For years, scientists have speculated about how and when the first galaxies formed, but until the arrival of JWST, the evidence has been scarce. The light emitted by the universe's first galaxies was so faint and distant that it was nearly impossible to observe with older telescopes. But with the advent of JWST, we now have a clearer picture of the early universe. This new galaxy, seemingly born in the early days of cosmic history, challenges many of the assumptions that were held about how galaxies evolve. Could the galaxy have formed in a way that bypassed the traditional slow accumulation of mass and structure? Could it have been influenced by some unknown cosmic force, or by interactions with neighboring galaxies, that allowed it to develop more rapidly? The rapid emergence of this galaxy raises more questions than it answers, but it also opens up new avenues of research into the nature of the early universe. One of the biggest mysteries that this discovery brings into focus is the role of dark matter in the early universe. Dark matter, the invisible substance that makes up most of the mass in the universe, has long been a crucial component in the formation of galaxies. It is believed to provide the necessary gravitational pull for galaxies to coalesce. But dark matter's role in the early universe is still poorly understood. Was dark matter more active during the formation of the first galaxies than we previously thought? Could dark matter have helped catalyze the rapid formation of galaxies like the one discovered by JWST? Perhaps dark matter didn't just provide the gravitational scaffolding for galaxies to form. Perhaps it played a more direct role in their rapid growth. The implications for our understanding of dark matter are profound, as this discovery suggests that it may have behaved in ways that were previously unforeseen. In addition to dark matter, the discovery also invites a re-evaluation of the role of dark energy in the early universe. Dark energy, the mysterious force that is driving the accelerated expansion of the universe, has been thought to influence the growth and spread of cosmic structures. Could it have played a more active role in the formation of galaxies, allowing them to emerge more quickly? Could it be that the forces that govern the expansion of the universe were not only shaping the cosmos on large scales but also driving the formation of smaller structures in ways we don't fully understand? The discovery of this galaxy suggests that the forces of the early universe may have been far more complex than we previously imagined. This galaxy, in a sense, holds the key to unlocking many of the universe's most elusive secrets. Its discovery is a reminder that we are only beginning to scratch the surface of cosmic history. As astronomers continue to study this galaxy and others like it, they will undoubtedly uncover more information about the early universe, how it evolved, how galaxies formed, and what forces were at play. We may also come to realize that there are more surprises waiting for us, hidden in the far reaches of space, just as this galaxy was hidden until JWST uncovered it. The universe is vast and full of mysteries, and this discovery is just one of many that will continue to challenge and expand our understanding of the cosmos. Ultimately, the discovery of this galaxy serves as a reminder of the profound nature of scientific inquiry. Every new discovery raises new questions, forces us to confront our assumptions, and challenges us to look deeper into the unknown. The mystery of the early universe, once thought to be out of our reach, is now becoming more accessible, and with each new discovery, we draw closer to understanding the true origins of everything. This galaxy is not just an anomaly in the distant past. It is a window into the universe's most enigmatic and transformative era. It is a glimpse into the cosmic dawn, a time of both wonder and uncertainty, when the first galaxies took shape and the universe began to reveal its deeper mysteries. As we continue to explore this new frontier, we are reminded that the universe holds more secrets than we can imagine, and that each discovery brings us one step closer to understanding the origins of it all. The discovery of this extraordinary galaxy by the James Webb Space Telescope raises far more than just questions about cosmic structure. It invites us to consider the very forces that drive the formation of galaxies themselves. While much of our understanding of galaxy formation comes from observations of light, matter, and gravity, a deeper understanding lies in the realm of high-energy physics, the study of the fundamental particles and forces that govern the universe at the smallest scales. High-energy physics has long been at the frontier of cosmic exploration, providing the theoretical framework for understanding the universe's earliest moments. This discovery forces us to consider how these high-energy processes may have played a more direct role in the rapid emergence of galaxies, especially those that, like the one discovered by JWST, don't fit into our current understanding of cosmic evolution. At the heart of high-energy physics lies the study of fundamental particles and the interactions that govern their behavior. The standard model of particle physics, which describes the known fundamental particles and forces, except for gravity, has provided a comprehensive understanding of the microscopic universe. The four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, work together to shape everything from the smallest atoms to the largest cosmic structures. However, it is the first few moments of the universe, during and immediately after the Big Bang, that remain the most mysterious. During this time, temperatures and energies were so extreme that the usual laws of physics as we understand them broke down. It was a time when the fundamental forces and particles existed in a state far more energetic than anything we experience today. The very beginning of the universe was a period of high-energy physics in its most intense form. In the first moments after the Big Bang, particles were in a highly energetic state, constantly interacting and exchanging energy. The universe was so hot that atoms, molecules, and even protons and neutrons could not exist in their present form. Instead, matter was in a state of quark-gluon plasma, a high-energy soup of fundamental particles that would eventually cool and combine to form the building blocks of matter. As the universe expanded and cooled, the particles began to organize into protons, neutrons, and electrons, eventually forming atoms, stars, and galaxies. While the rapid cooling and expansion of the universe were pivotal in shaping cosmic evolution, it was the behavior of high-energy particles during this time that set the stage for the formation of galaxies. The conditions of the early universe were extreme, and it is here that high-energy physics holds particular relevance. The behavior of particles, the interaction of fundamental forces, and the role of dark matter and dark energy all intertwine at this critical juncture in the universe's history. Understanding how these high-energy processes shaped the formation of the first galaxies is essential for understanding the rapid emergence of structures like the one discovered by JWST. High-energy physics also comes into play when we consider the role of dark matter in galaxy formation. Dark matter, which makes up a significant portion of the universe's mass, does not interact with light or normal matter in the same way that ordinary matter does, making it nearly invisible to our instruments. Despite its elusive nature, dark matter's presence is inferred by its gravitational effects on visible matter. Its role in galaxy formation has long been suspected, and high-energy physics helps us understand how dark matter could have contributed to the rapid formation of this galaxy. Dark matter's gravitational influence provides the scaffolding for galaxies to form, helping to bind stars and gas together, but its exact properties, its particles, interactions, and behavior, remain a mystery. One of the leading candidates for dark matter is a class of hypothetical particles known as WIMPs, weakly interacting massive particles. These particles, if they exist, could provide the gravitational pull needed to form galaxies in the early universe. However, WIMPs and other dark matter candidates interact so weakly with normal matter that detecting them directly is extraordinarily difficult. This is where high-energy physics experiments, such as those conducted at particle accelerators like the Large Hadron Collider, LHC, come into play. These experiments attempt to recreate the conditions of the early universe, allowing scientists to observe the behavior of fundamental particles and their interactions. By studying these interactions, scientists hope to uncover the properties of dark matter and learn more about how it influenced the formation of galaxies. The discovery of this galaxy might suggest that dark matter played a more central role in galaxy formation than previously thought. If galaxies can form in such an accelerated manner, it may be that dark matter acted as a sort of cosmic catalyst, influencing the formation of structures more quickly and efficiently than we have assumed. If dark matter's influence was more immediate and powerful, it could help explain how this galaxy formed so rapidly, seemingly out of nowhere. The early universe was an extremely chaotic place, with a large amount of energy and matter interacting in complex ways. High-energy processes at this stage could have led to the formation of dense regions of dark matter, which in turn would have accelerated the growth of galaxies. Another critical aspect of high-energy physics in the early universe is the interaction of electromagnetic radiation with matter. During the first few 100,000 years after the Big Bang, the universe was filled with a hot, dense plasma of free electrons and atomic nuclei. This plasma prevented light from traveling freely, resulting in a universe that was opaque to radiation. As the universe cooled, atoms formed, and the plasma recombined into neutral hydrogen, allowing photons to travel freely for the first time. This marked the end of the recombination era and the beginning of what we observe today as the cosmic microwave background radiation. The CMB is the afterglow of the Big Bang and provides a snapshot of the universe as it was roughly 380,000 years after the event. However, as galaxies began to form, they also began emitting radiation that influenced their environment. The intense energy released by the first stars and galaxies caused a process known as reionization, where the ultraviolet radiation from these stars ionized the surrounding hydrogen gas. This process reheated the universe and led to the creation of ionized bubbles in the cosmic gas. The study of reionization and its effects on galaxy formation is an active area of research, as it is believed that the interplay between high-energy radiation and the surrounding gas could have accelerated the growth of galaxies. The rapid formation of this new galaxy challenges our current understanding of this process. How could a galaxy, which is so massive and complex, form so early in the universe's history? The interplay of high-energy processes, dark matter, radiation, and gravitational forces, likely acted in concert to create a faster, more dynamic model of galaxy formation than we have previously considered. Understanding how these high-energy forces shaped the formation of this galaxy could provide crucial insights into the early universe, revealing a more intricate and complex picture of how the cosmos evolved. As astronomers continue to study this galaxy, they will undoubtedly turn to high-energy physics to help explain its rapid emergence. The discovery serves as a reminder that the universe operates on multiple scales, from the smallest particles to the largest structures, and that understanding the fundamental forces that govern these scales is essential for understanding cosmic evolution. This galaxy, with its unusual size and maturity, could serve as a crucial clue in unraveling the mysteries of dark matter, high-energy physics, and the early universe, providing a deeper understanding of the forces that shape the cosmos. Ultimately, the role of high-energy physics in understanding galaxy formation underscores the interconnectedness of the universe's various forces and particles. The discovery of this extraordinary galaxy is not just an observational triumph. It is a gateway to exploring the deeper, more fundamental mechanisms at play in the cosmos. By studying how high-energy processes contributed to the rapid formation of galaxies, scientists may soon be able to rewrite the story of the universe's evolution, one that goes beyond the visible structures we observe today and delves into the very particles and forces that shaped its creation. The universe's secrets, it seems, are hidden in the smallest of places, and high-energy physics may be the key to unlocking them. The discovery of this extraordinary galaxy not only challenges our understanding of how galaxies evolve but also places a spotlight on one of the most profound mysteries in modern astrophysics: the search for the first stars and their role in shaping the universe as we know it. The early universe, a time of great turbulence and transformation, was populated by a vast and unknown sea of gas, dark matter, and primordial radiation. It is during this early period, shortly after the Big Bang, that the first stars, known as population 3 stars, are believed to have emerged, igniting a cascade of events that would ultimately lead to the formation of galaxies, stars, and planets. For years, scientists have theorized about the birth of these first stars, but observing them has proven to be one of the greatest challenges in astronomy. These stars, if they exist, are thought to have been composed of only the simplest elements, hydrogen and helium, formed in the first few 100 million years of the universe's history. Unlike stars today, which are rich in heavier elements like carbon, oxygen, and iron, population 3 stars would have been much larger, hotter, and brighter. They would have burned through their fuel much faster, leaving behind massive black holes or even supernovae. These stars are thought to have played a pivotal role in the development of the universe, as they were responsible for reionizing the gas that filled the universe, allowing light to travel freely for the first time and marking the end of the cosmic dark age. The search for these first stars has long been a central focus of astronomers. The cosmic dark age, the period that followed the Big Bang when the universe was filled with neutral hydrogen gas and devoid of any stars or galaxies, lasted for hundreds of millions of years. During this time, the universe was opaque to light, and no sources of radiation existed to illuminate the dark expanse. But as the first stars began to form, they unleashed ultraviolet radiation that ionized the surrounding hydrogen gas, making the universe transparent once more. This era, known as reionization, was a turning point in cosmic history, and understanding it is crucial to understanding the formation of galaxies, stars, and the conditions that led to the universe we see today. However, this critical phase in cosmic evolution has remained largely hidden from view. The light from the first stars is incredibly faint and redshifted, meaning that by the time it reaches us, it has been stretched out over billions of years, making it extremely difficult to detect. The James Webb Space Telescope, with its unparalleled sensitivity and ability to observe infrared wavelengths, has finally begun to pierce through the fog of the early universe. As a result, astronomers are now able to study galaxies that formed in the first few 100 million years after the Big Bang, potentially giving us a glimpse of the first stars. The galaxy discovered by JWST is an intriguing candidate in this search. Its unexpected size and maturity suggest that it may have formed from or in the presence of population 3 stars or their remnants. This raises an important question. Could this galaxy be an example of the first galaxy formed after the birth of the first stars? And if so, what does it tell us about the relationship between galaxies and these primordial stellar bodies? The fact that this galaxy seems to be so developed so early in cosmic history suggests that the formation of galaxies may have been influenced directly by the processes initiated by the first stars, providing new insights into the interplay between stars, gas, and dark matter during the universe's formative years. As astronomers study this galaxy further, they will look for signs of the earliest stellar populations, particularly population 3 stars, within it. These stars are thought to have left behind unique signatures in the gas surrounding them, such as certain chemical elements that were not present in the universe until these stars began to burn through their nuclear fuel. By studying the light emitted by this galaxy, scientists hope to uncover traces of these first-generation stars, providing a vital piece of the puzzle in our understanding of how the universe's first galaxies came to be. One of the most intriguing aspects of the first stars is their potential to have played a key role in the process of reionization. The intense radiation from population 3 stars would have been responsible for ionizing the hydrogen gas that filled the universe, leading to a sudden increase in the visibility of the cosmos. This process, known as the reionization epoch, was a defining moment in the universe's evolution, as it set the stage for the formation of more complex cosmic structures, such as galaxies and clusters of galaxies. Without the energy released by the first stars, the universe would have remained in a state of darkness for a much longer period, and the formation of galaxies as we know it may not have been possible. The study of this galaxy may offer crucial insights into the role of population 3 stars in this critical epoch. If this galaxy was formed from the remnants of the first stars, it could provide a direct link between the birth of galaxies and the onset of reionization. By studying its chemical composition, its age, and its structure, scientists can begin to piece together the timeline of cosmic evolution and understand how the first stars set the stage for the complex cosmic tapestry we observe today. There are also implications for our understanding of star formation in general. If galaxies can form in a mature state much earlier than we thought, as this newly discovered galaxy suggests, it could mean that the processes that drive star formation are more efficient and rapid than we previously assumed. This could point to new, undiscovered factors in the early universe that facilitated the birth of the first stars and galaxies. Perhaps the conditions in the early universe were more conducive to star formation, or perhaps there were other, unknown sources of energy that helped trigger the rapid growth of cosmic structures. The discovery of this galaxy may prompt a re-evaluation of the factors that influence star formation, not just in the early universe but in galaxies today. Moreover, this discovery raises an important question about the future of the universe. If galaxies like the one discovered by JWST could form so quickly in the early universe, does this imply that the same processes could lead to the creation of new stars and galaxies in the future? Could the universe still be in a state of constant evolution, where new structures are born from the ashes of the old? Or have we already reached a point in cosmic history where the major processes of galaxy formation have largely concluded, and the universe is in a period of quiet expansion? The discovery of such a massive, fully formed galaxy in the distant past suggests that the universe is far from static. It is an ever-evolving system, constantly reshaping itself in ways that we are only beginning to understand. Ultimately, the search for the first stars and their role in cosmic evolution is a search for the origins of everything we know. The first stars ignited the process of galaxy formation and provided the energy needed to light up the universe. They are the cosmic progenitors, the seeds from which everything else grew. This discovery, and the possibility that the galaxy observed by JWST may have formed in the presence of these primordial stars, brings us closer to understanding that foundational moment in cosmic history. As we continue to study this galaxy and others like it, we are one step closer to unraveling the mystery of how the universe evolved from its early dark infancy into the vibrant and complex system of stars and galaxies we observe today. The first stars are not just a point in time, they are the key to understanding the very nature of the universe's creation, and the discoveries ahead will help to shed light on one of the most important chapters in the story of the cosmos. The discovery of this massive and seemingly well-developed galaxy, emerging so early in the universe's history, forces a fundamental reassessment of the cosmic timeline. For decades, astronomers and cosmologists have relied on the framework of the Big Bang theory to guide their understanding of the universe's evolution. According to this widely accepted model, the universe began in a hot, dense state and gradually expanded, with galaxies and stars forming much later in cosmic history. The traditional timeline suggests that the first galaxy started to take shape hundreds of millions of years after the Big Bang, with stars and stellar clusters slowly coalescing over time. However, the discovery of this ancient, highly evolved galaxy shatters this conventional narrative, forcing scientists to rethink the processes that govern the early universe and the rate at which galaxies could form. At the heart of this new perspective is the realization that galaxy formation may not have been as gradual and slow as once thought. The vast scale of the universe and its underlying physical laws suggest that the formation of galaxies and large-scale structures was driven by forces that acted more quickly than previously imagined. In this new view, galaxies may have rapidly formed in the early universe, evolving at a pace far faster than what conventional models have suggested. This raises profound questions about the nature of cosmic evolution, the role of dark matter, and the complex interplay of forces that shape the universe's history. The traditional cosmic timeline, built on the Big Bang theory and the expansion of the universe, posited that the first galaxies emerged from small, fragmented clouds of gas and dust, gradually growing over time. These early galaxies were thought to be chaotic, irregular in shape, and composed primarily of hydrogen and helium. They were the seeds from which the universe's later galaxies would grow. Over billions of years, stars formed within these galaxies, evolving into the spiral, elliptical, and irregular galaxies we see today. But the galaxy discovered by JWST defies this model by appearing much larger and more complex than expected for such an early point in cosmic history. Instead of being a chaotic, nascent cloud of matter, this galaxy seems to be fully formed, with evidence of ongoing star formation, and yet it exists at a time when it should still have been in its infancy. The presence of such a large and well-formed galaxy so early in the universe challenges the prevailing view of cosmic evolution, and the implications are staggering. One possibility is that the early universe experienced an accelerated period of growth, where galaxies formed much more quickly than our current models suggest. This would imply that the mechanisms responsible for galaxy formation were far more efficient in the early universe. In this scenario, instead of taking billions of years for galaxies to assemble, they may have emerged within just a few 100 million years after the Big Bang, driven by faster gravitational collapse, more efficient accretion of gas, or some other process not yet fully understood. This idea suggests that the formation of galaxies could have been punctuated by rapid bursts of activity, rather than the gradual, steady growth previously assumed. Instead of a slow accumulation of stars and gas over billions of years, galaxies may have reached their current sizes through a much more dynamic process. The early universe may have been a time of extreme turbulence, with high levels of cosmic radiation, more intense gravitational forces, and more rapid cooling, all of which could have triggered bursts of star formation and galaxy assembly. This rapid formation could be tied to the presence of dark matter, which plays a key role in the formation of galaxies by providing the necessary gravitational pull to help accumulate matter. Dark matter's role in these early cosmic events might have been far more significant than we previously realized, acting as both a scaffold and a catalyst for the formation of galaxies in a much shorter time than originally thought. Another possibility is that the cosmic dark age, the period after the Big Bang when the universe was largely filled with hydrogen and helium and devoid of light, may not have lasted as long as previously believed. According to current models, the universe remained in this dark state for several 100 million years before the first stars began to shine. But if galaxies like the one discovered by JWST can form in such a short time, it suggests that the process of reionization, when the universe's first stars began to ionize the surrounding hydrogen gas, allowing light to travel freely, might have begun much earlier. This could imply that the early universe underwent a more rapid transformation, with stars and galaxies emerging in bursts, reshaping the cosmos at an accelerated rate. Such a paradigm shift would not only change our understanding of the timeline of cosmic history but also prompt a re-evaluation of the forces that drove this rapid evolution. The discovery also raises questions about the relationship between galaxies and supermassive black holes. Supermassive black holes are thought to lie at the centers of most galaxies, and their growth is believed to be closely tied to the evolution of their host galaxies. In the case of the galaxy discovered by JWST, if it is indeed so mature and large at such an early time, it may be that supermassive black holes played a significant role in its rapid formation. These black holes could have acted as both a source of energy and a catalyst for star formation, driving the creation of new stars while simultaneously consuming large amounts of surrounding gas and dust. This intricate relationship between galaxies and their central black holes could be key to understanding how galaxies evolve and grow so quickly in the early universe. This new discovery also brings to light the role of cosmic inflation in shaping the universe's early history. Cosmic inflation, a period of rapid expansion that occurred just moments after the Big Bang, is thought to have set the initial conditions for the universe's large-scale structure. Inflation caused regions of space to expand exponentially, smoothing out irregularities and allowing for the eventual formation of galaxies, stars, and other cosmic structures. But if galaxies were able to form more quickly than previously expected, it may suggest that the mechanisms driving inflation or the early expansion of the universe were more complex than we realized. Perhaps inflation not only shaped the large-scale structure of the universe but also had a more direct impact on the formation of galaxies, providing the necessary conditions for their rapid creation. As we continue to study the galaxy discovered by JWST, scientists will seek to refine and expand their models of cosmic evolution. The discovery challenges our existing notions of how galaxies form and evolve, urging researchers to develop new theories that can account for this galaxy's unusual size and maturity. Perhaps the traditional linear model of cosmic history, where galaxies evolve slowly over billions of years, needs to be replaced with a more dynamic, burst-driven model, in which galaxies emerge more quickly in certain conditions. This would necessitate a rethinking of how galaxies interact with their environment, how dark matter contributes to their formation, and how cosmic radiation influences the development of stars and galaxies. The new paradigm of galaxy formation that emerges from this discovery will likely have profound implications not only for our understanding of the universe's early history but also for our models of galaxy formation and evolution moving forward. By revising the timeline of cosmic evolution, we can gain deeper insights into the processes that govern the birth of galaxies, the role of dark matter, and the mechanisms that allowed the universe to evolve from a hot, dense state into the vast, complex structure we observe today. As we continue to explore the universe through the lens of the James Webb Space Telescope and other cutting-edge instruments, we may uncover even more surprising discoveries that force us to rewrite our understanding of the cosmos. The universe, it seems, has far more surprises in store than we could have ever imagined. The discovery of this unusually large and mature galaxy, formed so early in the universe's history, has profound implications for our understanding of dark matter and dark energy, two of the most mysterious components of the cosmos. These invisible substances make up about 95% of the universe's total mass and energy content, yet they remain largely undetectable through conventional means. The galaxy observed by JWST, with its unexpected size and complexity at such an early stage, raises questions about how dark matter and dark energy may have influenced the formation and rapid evolution of galaxies in the early universe. Dark matter, which does not emit, absorb, or reflect light, is inferred to exist based on its gravitational effects on visible matter. It is thought to be a fundamental player in the formation of galaxies, as its gravitational pull helps clump matter together, providing the scaffolding for galaxies to form and grow. However, the exact nature of dark matter is still unknown. The discovery of a galaxy that is so well formed so early in cosmic history could suggest that dark matter played a more central role in the rapid formation of such galaxies than we previously thought. Could dark matter have been more abundant or more concentrated in the early universe, acting as a kind of cosmic glue that accelerated the assembly of galaxies? This could lead to a rethinking of the role dark matter plays not only in the present universe but also in the universe's early stages, where its influence may have been far more pronounced. Dark energy, the mysterious force that is accelerating the expansion of the universe, has its own role to play in this story. While dark energy is most often associated with the large-scale expansion of the universe, its influence may have had subtle effects on the formation of structures like galaxies. If the expansion rate of the universe was different in the past, perhaps dark energy influenced the way galaxies formed or interacted with each other. The discovery of this galaxy so early in the universe's history raises the possibility that dark energy could have had a more active role in shaping the cosmos than we previously believed. This finding invites a re-evaluation of how these two cosmic phenomena, dark matter and dark energy, work together, potentially influencing the speed at which galaxies form, grow, and evolve. Could they have acted in concert to produce the rapid emergence of galaxies like the one seen by JWST? Or are there other unknown forces at play in the early universe that have yet to be discovered? As scientists continue to explore these questions, the discovery of this galaxy adds a new layer of complexity to our understanding of the universe's most enigmatic components. Over time, galaxies formed into clusters, which were the building blocks of even larger structures called superclusters. These superclusters are the largest known structures in the universe, containing thousands of galaxies bound together by gravity. The formation of superclusters was the result of the same gravitational forces that shaped galaxies, but on an even larger scale. These enormous structures, in turn, influenced the movement and behavior of galaxies within them, leading to further interactions and mergers. The study of cosmic structures like superclusters is essential for understanding the evolution of the universe. While galaxies are the fundamental building blocks of the cosmos, they do not exist in isolation. They are part of a vast and interconnected web of matter, with gravitational forces shaping their interactions. This web is what gives the universe its large-scale structure and is key to understanding how galaxies and other cosmic structures formed and evolved over time. The rapid formation of this newly discovered galaxy provides a unique opportunity to study the mechanisms that drive the birth of complex structures in the universe. By analyzing its composition, age, and structure, scientists can gain new insights into the processes that led to its creation. This galaxy may offer a window into the early stages of galactic formation, revealing details about how galaxies form, merge, and evolve in the primordial universe. In conclusion, the emergence of complex structures in the universe is a fascinating and ongoing process, shaped by the forces of gravity, dark matter, and radiation. The birth of galaxies, stars, and other cosmic objects is a critical part of the story of the universe, and the discovery of this rapidly forming galaxy challenges our understanding of how these structures evolve. Whether through mergers, the influence of dark matter, or the effects of the first stars, galaxies and other cosmic structures continue to form and evolve, revealing the intricate beauty of the universe's ongoing evolution. As we continue to study these complex systems, we move ever closer to understanding the fundamental forces that have shaped the cosmos. The discovery of this ancient galaxy also sheds light on one of the most crucial and transformative epochs in the history of the universe: reionization. This period, which occurred roughly 400 million years after the Big Bang, marks the moment when the first stars and galaxies began to emit ultraviolet radiation, which ionized the surrounding hydrogen gas, allowing light to travel freely across the universe for the first time. Reionization fundamentally altered the state of the universe, transitioning it from an opaque, dark expanse to a transparent one filled with light. The significance of this process cannot be overstated, as it set the stage for the formation of the galaxies and cosmic structures that populate the universe today. Before reionization, the universe was in a state known as the Cosmic Dark Age, a time when there were no stars or galaxies to light up the universe. During this period, the universe was filled with a dense fog of neutral hydrogen and helium gas. Without any sources of light, the universe remained a dark, featureless expanse. As the first stars, population 3 stars, began to form and shine, their ultraviolet radiation began to break apart the hydrogen atoms in the surrounding gas, stripping away their electrons and creating ionized regions. This process of reionization spread throughout the universe, eventually allowing light to travel freely and marking the end of the Cosmic Dark Age. The galaxy discovered by JWST may provide valuable insights into the timing and mechanics of this process. Its unexpected size and maturity suggest that it could have been formed during or shortly after the reionization epoch. If this galaxy was able to form so quickly and with such complexity, it could indicate that the reionization process was more rapid and widespread than previously thought. This discovery might also suggest that galaxies began forming at an accelerated pace during this critical period, potentially reshaping our understanding of the timeline of the early universe. Reionization is believed to have been a gradual process, with some regions of the universe being ionized earlier than others, but the new evidence presented by this galaxy suggests that galaxies may have been forming much earlier and more efficiently than previously assumed. The presence of this galaxy at such an early stage of cosmic history indicates that the conditions necessary for galaxy formation, such as the ionization of hydrogen gas, were present much sooner than expected. This discovery invites new questions about the connection between the ionization process and the rapid formation of galaxies. How did the radiation from the first stars influence the surrounding gas? Did reionization trigger or accelerate the formation of galaxies, or did galaxies form in parallel with reionization, each influencing the other? By studying this galaxy and others like it, astronomers hope to refine their models of reionization and its role in shaping the early universe. This epoch was one of the most important in cosmic history, as it set the stage for the formation of the first galaxies, stars, and ultimately the universe as we know it. The discovery of this galaxy provides a unique opportunity to study the processes that shaped the universe's transition from a dark, featureless expanse to the dynamic, illuminated cosmos we observe today. As we continue to unravel the mysteries of galaxy formation, one of the most intriguing and perplexing questions revolves around the role of supermassive black holes. These enigmatic objects, which reside at the centers of most galaxies, possess masses millions or even billions of times greater than that of the Sun. The connection between supermassive black holes and the galaxies that host them is a fundamental aspect of our understanding of cosmic evolution, yet the precise relationship between the two remains unclear. The discovery of this massive and unexpectedly mature galaxy, so early in the universe's history, adds a new layer of complexity to this ongoing puzzle. Supermassive black holes are believed to play a crucial role in the formation and evolution of galaxies. Their immense gravitational pull influences the dynamics of the galaxy's central region, shaping the motions of stars, gas, and dust. These black holes are also thought to drive the process of active galactic nuclei, AGN, where material falls into the black hole, releasing enormous amounts of energy in the form of radiation. This energy can in turn have a significant impact on the surrounding galaxy, regulating star formation and influencing the overall growth of the galactic structure. The presence of such a well-formed galaxy at such an early epoch raises the possibility that supermassive black holes may have played a pivotal role in shaping its rapid formation. The relationship between supermassive black holes and galaxy formation is thought to be a mutual one. As galaxies form, it is believed that the matter and gas that congregate at the galaxy's center eventually give birth to a supermassive black hole. Over time, as the black hole accretes more material, it grows in size and mass, influencing the galaxy's evolution in profound ways. However, the process by which these black holes form and grow in the early universe remains one of the greatest unsolved mysteries in cosmology. How did these supermassive black holes come into existence so quickly? What triggered their rapid growth in the early stages of the universe? The galaxy observed by JWST might offer clues to these questions. If this galaxy is indeed as mature as it appears, it suggests that a supermassive black hole could have played a role in its early development. In the early universe, the presence of a black hole could have triggered intense bursts of star formation and driven the release of enormous amounts of radiation. This energy could have influenced the surrounding gas, accelerating the formation of stars and contributing to the galaxy's rapid growth. The black hole might have been a driving force in the galaxy's evolution, exerting gravitational influence over the surrounding matter and regulating the rate of star formation. This also raises important questions about the timescale of black hole formation. Supermassive black holes are thought to form through a combination of processes, including the collapse of massive clouds of gas, the merging of smaller black holes, and the accretion of material over time. In the early universe, the conditions for black hole growth may have been vastly different from those we observe today. The density of gas, the availability of matter, and the intensity of radiation could have all played a role in accelerating the formation of these massive objects. The discovery of a galaxy with such a well-formed structure suggests that supermassive black holes could have grown much faster than previously thought, challenging our assumptions about the timescales of black hole and galaxy evolution. Furthermore, the discovery invites a re-examination of the feedback mechanisms between galaxies and their central black holes. As black holes grow, they release enormous amounts of energy, which can drive powerful outflows of gas and limit the growth of the galaxy by preventing the accumulation of further gas. This feedback loop between black holes and galaxies is thought to play a crucial role in regulating galaxy evolution. Could it be that the rapid formation of galaxies in the early universe was closely tied to the feedback from supermassive black holes? If black holes grew faster and more efficiently than we currently understand, they may have played a crucial role in shaping the early universe, regulating the rate of galaxy formation, and influencing the growth of cosmic structures in ways we have yet to fully comprehend. The relationship between supermassive black holes and galaxy formation remains one of the central puzzles in cosmology, and the discovery of this ancient galaxy provides a potential window into this mystery. As we continue to study the galaxy, its central black hole, and the surrounding environment, we may uncover new insights into how supermassive black holes formed so quickly in the early universe and how they influenced the rapid growth of galaxies. The presence of a mature galaxy at such an early stage in the universe's history suggests that the evolution of galaxies and black holes may have been more interconnected and more dynamic than previously imagined. This discovery challenges our current models of cosmic evolution and opens up exciting new avenues of research into the nature of black holes, galaxies, and the universe itself. The discovery of this early, highly evolved galaxy has profound implications that reach far beyond the specific galaxy in question. It demands that cosmologists rethink long-established theories about the formation of galaxies, the role of dark matter, and the timeline of the universe's evolution. What was once considered a well-understood narrative of cosmic history is now being challenged by new data that suggest the processes governing galaxy formation and evolution may be far more complex and dynamic than we have previously imagined. The rapid emergence of this galaxy forces scientists to confront several key questions that go to the very heart of cosmological theory. For instance, the speed at which this galaxy formed suggests that galaxies may have evolved much faster than the conventional models predict. In these models, galaxies form gradually over billions of years, with the initial conditions set by the Big Bang and cosmic inflation. However, the maturity of this galaxy suggests that rapid formation might have been possible in the early universe, potentially indicating that the processes behind galaxy formation are more efficient than previously thought. This discovery also raises important questions about the nature of dark matter and its role in the early universe. Traditional models suggest that dark matter acted as a passive scaffold, providing the gravitational pull necessary for galaxies to form. However, the existence of such a large and well-formed galaxy at such an early stage could suggest that dark matter might have been more active in facilitating galaxy formation. Perhaps dark matter didn't just act as a passive player but as an active catalyst, influencing the rate of collapse and galaxy assembly. This shift in perspective could lead to new theories that explore the more dynamic interaction between dark matter and ordinary matter, challenging the notion of dark matter as merely an invisible scaffold and suggesting that its role in galaxy formation is far more profound. Additionally, the discovery calls into question the traditional understanding of the cosmic timeline. If galaxies can form so rapidly in the early universe, what does that mean for our understanding of cosmic history? Was there a cosmic jumpstart that accelerated the formation of galaxies, or were the conditions in the early universe far more conducive to rapid formation than we had imagined? Perhaps we need to rethink the entire timeline of cosmic evolution, considering that galaxies could have been forming much earlier than previously believed. The discovery of this galaxy suggests that new mechanisms, some yet undiscovered, may have played a significant role in accelerating galaxy growth during the first few 100 million years after the Big Bang. As scientists begin to refine and develop new models in response to this discovery, the field of cosmology is entering a period of exciting transformation. The current understanding of galaxy formation, dark matter, and cosmic evolution is being tested, and it is likely that these new findings will lead to the development of more complex, nuanced theories that can account for the surprising realities of the early universe. Just as the discovery of cosmic inflation radically reshaped our understanding of the Big Bang, so too might this galaxy's unexpected existence force a rethinking of the very forces that shape the universe. The implications of this discovery extend far beyond a single galaxy. They have the potential to rewrite our understanding of the cosmos itself, prompting a paradigm shift in the way we conceive of the universe's origins and evolution. The discovery of a galaxy that is both vast and fully formed at such an early stage of the universe presents an array of unanswered questions that challenge our current understanding of cosmology and astrophysics. While this finding has provided new insights into the complexities of galaxy formation, it also opens the door to a multitude of mysteries that scientists are now eager to explore. What forces or mechanisms allowed this galaxy to evolve so rapidly? Was this discovery a fluke, or do other galaxies from the same epoch share similar characteristics? And perhaps most importantly, how do these revelations shape our broader understanding of the universe? The first major question that arises is how such an early galaxy could reach such a high level of maturity. According to conventional theories, galaxies are expected to grow gradually over billions of years, beginning as small, irregular structures of gas and dust. This particular galaxy, however, appears to have bypassed this gradual growth, emerging in a more fully developed state with ongoing star formation. What triggered such rapid growth? Could there have been environmental factors, such as the density of dark matter, the presence of a nearby quasar, or unique conditions in the cosmic web, that allowed for such accelerated galaxy formation? The nature of these factors remains unknown, but this discovery suggests that some unknown cosmic processes may be at work, ones that science has yet to uncover. Another question that looms large is whether this galaxy is an anomaly or whether similar galaxies will be discovered as more data is gathered. The James Webb Space Telescope has only just begun to probe the far reaches of the universe, and it is likely that other galaxies with similar properties exist, hidden in the depths of space. The key question here is whether this galaxy represents an outlier or if its rapid evolution is indicative of a broader pattern in the early universe. If other galaxies from the same epoch share similar traits, it would require a major revision of current models of galaxy formation and evolution. This discovery may be the tip of the iceberg, a glimpse into a far more complex and dynamic early universe than we had previously imagined. The relationship between dark matter and galaxy formation also remains a critical area of inquiry. While dark matter is thought to provide the gravitational scaffolding for galaxies to form, the exact ways in which it interacts with ordinary matter are still largely speculative. This galaxy's rapid growth suggests that dark matter could play a more active and dynamic role in galaxy formation than previously assumed. How does dark matter affect the rate at which gas and dust collapse into stars? Can its gravitational influence accelerate or even catalyze the formation of galaxies? Understanding the precise role of dark matter in the formation of such early, mature galaxies will be crucial in reshaping our cosmic models. Finally, The most profound question of all is what these discoveries mean for our understanding of the universe's evolution. If galaxies could form at such an accelerated rate, does this imply that other cosmic phenomena such as star formation, black hole growth, or even the expansion of the universe itself, may have unfolded in ways we did not anticipate? The discovery of a highly developed galaxy so early in the universe suggests that the timeline of cosmic evolution may need to be rewritten. What we once thought of as a slow, gradual process of cosmic maturation might have been much more rapid, influenced by forces and conditions that we have yet to fully comprehend. As we continue to delve deeper into the mysteries of the universe with the help of advanced telescopes and observational technology, the unanswered questions surrounding this discovery will drive the next phase of exploration. The pursuit of answers to these questions promises to challenge and expand the boundaries of our understanding, reshaping the field of cosmology in ways that will continue to captivate scientists and the public alike for years to come. This galaxy is just one piece of a much larger puzzle, and its discovery signals the beginning of an exciting new chapter in our quest to understand the cosmos. As the James Webb Space Telescope continues to unveil the deepest corners of the universe, the future of galaxy research is entering a new and thrilling era. The discovery of a galaxy that defies conventional models by existing in a highly evolved state so early in the universe's history marks a pivotal moment for cosmology. It is only the beginning of what promises to be a revolution in how we study the formation and evolution of galaxies, stars, and the larger cosmic structures they inhabit. The next steps in this journey are not just about gathering more data, they will involve rethinking the very tools, theories, and paradigms that have long defined our understanding of the universe. One of the most exciting prospects is the continued use of the James Webb Space Telescope, which offers unprecedented capabilities for observing distant galaxies. With its powerful infrared sensors, JWST allows astronomers to peer back in time to a period just a few 100 million years after the Big Bang, a time previously hidden from view by the limitations of older telescopes. This capability will undoubtedly lead to more discoveries of galaxies in their infancy, providing further opportunities to test and refine our models of galaxy formation. JWST's sensitivity to infrared light also means that it can detect light from galaxies that are far too faint to be observed by visible light telescopes, enabling us to identify galaxies at various stages of evolution and piece together the puzzle of how they grew and developed. However, the power of JWST is not just in its ability to detect faint light from distant objects, but also in its ability to measure the physical properties of galaxies with unparalleled precision. By analyzing the light emitted by distant galaxies, astronomers can determine their age, chemical composition, star formation rates, and other crucial properties. This will allow for more detailed models of how galaxies form and evolve over time, especially in the early stages of cosmic history. As more galaxies like the one discovered in this study are observed, scientists will be able to test different theories of galaxy formation, examining whether rapid formation was a common phenomenon or an exceptional occurrence. Beyond JWST, the next wave of observational technologies will further push the boundaries of galaxy research. Ground-based observatories such as the Extremely Large Telescope (ELT) and the 30-meter telescope (TMT) are set to complement space-based missions, offering higher resolution images and more detailed data on the properties of galaxies. These observatories will allow scientists to study galaxies in even greater detail, looking at the motion of stars and gas, the behavior of supermassive black holes, and the role of dark matter in shaping these systems. Moreover, future missions could investigate the interactions between galaxies in ways that current technologies cannot. The merging of galaxies, an event that will shape the future evolution of the Milky Way, is a key area of study, and understanding how galaxies collide and coalesce into larger systems is critical to our understanding of cosmic history. Simulations of these mergers, combined with real observational data, will give us a deeper understanding of galaxy dynamics, star formation rates, and black hole growth during these cataclysmic events. As researchers gather more data and refine their models, the focus will also shift toward understanding the broader implications of galaxy evolution on the universe's large-scale structure. How do galaxies shape the cosmic web, the vast network of dark matter and gas that connects them? What can the distribution and motion of galaxies tell us about the expansion of the universe, dark energy, and the ultimate fate of the cosmos? These are questions that will drive the next generation of cosmological studies and guide our understanding of the universe on its largest scales. In parallel with observational advances, the development of new computational models will be essential. Simulating the complex processes of galaxy formation, including the role of dark matter, radiation, and supermassive black holes, will require more powerful supercomputers and refined algorithms. These models will allow scientists to test various hypotheses, simulate the birth and evolution of galaxies in different cosmic environments, and predict how galaxies will continue to evolve over the next few billion years. The future of galaxy research promises to be one of discovery and innovation, and the questions raised by the unexpected maturity of this early galaxy are just the beginning. With each new discovery, we move closer to understanding the true nature of the universe, how galaxies, stars, and dark matter came together to form the vast cosmic structure we observe today. As we continue to peer deeper into the cosmos, we are on the cusp of unveiling some of the most profound mysteries of existence. This is an exciting time for cosmology as new technologies, fresh perspectives, and groundbreaking discoveries combine to expand our understanding of the universe's past, present, and future. The discovery of this highly evolved galaxy at such an early stage in the universe's history opens a new frontier in cosmic exploration. As we uncover more mysteries of the early universe, this discovery lays the groundwork for future astronomical missions and advances in observational techniques that will help deepen our understanding of the cosmos. The implications of this finding reach far beyond the galaxy itself, influencing how scientists will approach the study of distant galaxies, dark matter, dark energy, and the fundamental processes that govern the birth of the universe. As the James Webb Space Telescope continues its groundbreaking work, and with upcoming missions like the Nancy Grace Roman Space Telescope and the next-generation ground-based observatories, this discovery points to an exciting era of cosmic exploration ahead. One of the key takeaways from this discovery is the sheer potential of the James Webb Space Telescope (JWST) to push the boundaries of our understanding. While the discovery of this early galaxy was a remarkable achievement in itself, it is just one example of the telescope's ability to peer deeper into the universe's past than ever before. JWST's unprecedented resolution and sensitivity to infrared light allow it to observe galaxies, stars, and cosmic structures that existed during the universe's infancy, providing insights into the formation of galaxies, star clusters, and even black holes. This discovery demonstrates that we may be on the verge of finding even more distant and ancient galaxies, many of which could challenge or even rewrite our current models of galaxy formation. JWST's continued operation will likely yield countless more discoveries, each one bringing us closer to understanding the fundamental nature of the universe. The importance of future missions extends beyond the capabilities of JWST alone. The upcoming launch of the Nancy Grace Roman Space Telescope, for instance, will complement JWST's findings by enabling large-scale surveys of the universe. Roman will provide detailed 3D maps of the universe's largest structures, helping to identify and analyze distant galaxies, dark matter, and dark energy. Together, Roman and JWST will allow scientists to study galaxies across a broad range of cosmic time, from the very first galaxies that formed after the Big Bang to those that are still evolving today. This synergy will offer a more complete picture of the universe's evolution and the processes that shape it. In addition to these space-based observatories, the development of next-generation ground-based telescopes will play a vital role in this new phase of cosmic exploration. Instruments like the Extremely Large Telescope (ELT), which is under construction in Chile, will have the capability to observe the first galaxies with incredible detail and precision. These telescopes will allow astronomers to study galaxy formation, star formation, and even the birth of supermassive black holes, providing critical data to support and complement findings from space-based observatories. As we look to the future, the discovery of this galaxy highlights the need for an integrated approach to cosmic exploration. The future of astronomy lies in the collaboration between ground-based and space-based telescopes, each offering unique capabilities that can complement one another. With the combined power of these advanced observatories, astronomers will be able to explore previously uncharted territories in cosmic history, uncovering more about the conditions that led to the rapid formation of galaxies and the mysterious forces that govern their evolution. This discovery also underscores the importance of multi-wavelength observations. By studying the universe across a broad spectrum of light, from radio waves to infrared, optical, and X-rays, astronomers can gather a more comprehensive view of the physical processes that govern galaxy formation. The combination of infrared observations from JWST and optical, ultraviolet, and X-ray observations from other telescopes will help to unravel the complex interactions between stars, gas, black holes, and dark matter. In conclusion, the discovery of this galaxy provides a crucial stepping stone in our journey to understand the early universe. It highlights the incredible potential of future astronomical missions and the importance of continuing to push the boundaries of exploration. With the next generation of space telescopes, ground-based observatories, and advanced data analysis techniques, we are entering a new era of cosmic discovery. The mysteries of galaxy formation, dark matter, dark energy, and the birth of the cosmos are closer than ever to being unlocked, and the future of cosmic exploration has never looked brighter. The discovery of this massive and well-developed galaxy so early in the universe's history is not only a milestone in cosmic research but also a profound reminder of the vastness and complexity of the cosmos. It challenges the foundations of our understanding of how the universe evolved, forcing us to re-examine the timeline of cosmic history, the mechanisms driving galaxy formation, and the forces that shape the birth of galaxies. But beyond its scientific implications, this discovery carries deeper philosophical and existential questions about humanity's place in the universe. What does it mean for our understanding of life, the nature of the cosmos, and the role we play within it? For centuries, humanity has been fascinated by the idea that we are part of something much greater than ourselves, something vast and incomprehensible, stretching beyond the limits of our senses. The discovery of galaxies forming at such an early stage in the universe's history emphasizes just how small and fleeting our place in this grand cosmic scheme may be. This galaxy, with its incredible size and maturity, formed billions of years ago, long before humanity, or even our solar system, came into existence. In the grand expanse of time, our lives, and even the entire history of human civilization, appear as mere blips. Yet, this realization does not diminish the awe that we feel when gazing at the stars. Rather, it underscores the incredible significance of human curiosity, exploration, and discovery. The pursuit of knowledge about the universe has always been intertwined with existential reflection. Every breakthrough in cosmic research invites us to reflect on our origins and our future. The discovery of a galaxy that defies our expectations of cosmic evolution forces us to ask how we fit into the ongoing story of the universe. Is our existence a rare fluke, a brief moment in an otherwise indifferent universe? Or is it part of a larger, ongoing process that is yet to unfold on scales of time and space far beyond our comprehension? In a sense, the more we discover about the universe, the more we realize how little we truly know. The universe operates on scales so vast, both spatially and temporally, that it remains largely beyond human understanding. This discovery, in revealing a galaxy that challenges our understanding of when and how galaxies can form, invites us to reconsider not only the cosmic timeline but also our own perceptions of time and space. It reminds us that the universe is dynamic, unpredictable, and always in motion, and that there is much left to explore. On a more practical level, this discovery emphasizes the role of science in expanding the horizons of human knowledge. In an era when scientific advancements seem to be progressing at an exponential rate, the discovery of distant galaxies by the James Webb Space Telescope represents the frontier of human exploration. Yet, this discovery also highlights the critical importance of collaboration, curiosity, and persistence in the pursuit of understanding. As scientists continue to observe the universe, the questions raised by this discovery will likely lead to new avenues of inquiry, new theories, new models, and new technologies that will help to further illuminate the mysteries of the cosmos. Perhaps one of the most profound implications of this discovery is the sense of wonder and humility it invokes in us. In the face of a universe so vast and ancient, it's easy to feel insignificant. Yet, it's precisely this vastness that makes our ability to understand and explore the universe so remarkable. This galaxy, like countless other discoveries in the history of science, serves as a reminder of the importance of pushing boundaries, seeking knowledge, and embracing the unknown. While we may never fully grasp the mysteries of the cosmos, every step forward in our understanding brings us closer to answering the most fundamental questions about our existence. Ultimately, this discovery calls upon humanity to reconsider its place within the universe, not as an isolated and fleeting moment but as part of a much larger cosmic tapestry, woven over billions of years. It challenges us to continue looking upward, to keep asking questions, and to seek knowledge that extends beyond our lifetimes. In doing so, we find not only answers to the questions about the cosmos but also a deeper understanding of ourselves. The universe is not only a place of great mystery and beauty, it is a reflection of the questions we ask and the curiosity that drives us to explore the unknown.